Good morning, sir.
Good morning. Just a second. So, are you trying the questions?
Yes, sir.
Okay.
So today atomic structure, sir.
A little topic, the percentage yield I told you, na, that was left for us to complete. Okay,
Yes, sir.
that we will finish and then we will go on
Okay,
to
sir.
the atomic structure.
Okay, sir.
Arey, why this guy is always late? Let me call him. Don't worry, Ram, about the timings. I can extend the class also, no issue. Okay.
Okay, sir.
If he joins, if let's see. If he doesn't join, then we will start.
Okay, sir.
So till that time, what I can do is I can write few questions for you regarding the percentage yield. Then we will
Okay.
discuss it. Okay.
Okay.
So the question number one says,
Sir, what is that before stoichiometry?
mm, stoichiometry. 1:1 ratio.
Okay.
Has Mrinal joined?
Yes, sir.
You joined?
Yes,
Okay.
sir.
Okay. I am just writing the questions right now. Few questions regarding some topic. Okay. The percentage yield.
Yeah, okay, sir.
Okay. So we will discuss this together. Let me write this. Finish this one. Please, guys, do the homework. If you want to score good in AP, please do the homework. Otherwise, it will be very difficult to score good in APs. Okay? Yeah, these two are the questions first of all. So, if you are noting it down, please do it fast, and I will start with the percentage yield concept. See, till now, Mrinal, have you watched the recording for the last lecture?
Sir, I did not, sir. I will watch it.
Array, then how will you understand this? Okay, you know the limiting region part, right?
Yes,
That
sir.
you know at
Limiting
least.
reagent, yeah.
Yeah, that you know, right? So okay, it's fine. Do you remember that? Do you all remember that we were calculating some uh, that how much a species is getting formed using the concept of limiting reagent, right?
Yes, sir.
Yeah.
Like in moles.
In moles, in grams, we can convert moles into grams as well, right?
Yes,
So
sir.
whatever you were calculating that time was your actual yield, was your theoretical yield, was your theoretical yield. So if you want to find out percentage yield, it is nothing but experimental yield divided by the theoretical yield. Theoretical yield. Now what do we mean by experimental yield? Okay, they will give you, let's say, theoretical yield. This you have to find out using your concepts of stoichiometry or limiting agent or whatever. Okay, this experimental yield, they will tell you that okay, one experiment was one reaction we were doing, and we got, let's say, 5 grams of a product y. Let's say y is the product which we got as 5 grams. Okay, like through the experiment, of course, if they are getting, if the question setter is getting as 5 grams, that will of course be the experimental yield which they are getting. Okay, so we need to find the theoretical yield ourselves, and then we will divide experimental yield by theoretical yield and multiply it by 100 to get a percentage yield. That in practice how much we should get, but how much we are getting in the experiments into 100 gives you the percentage yield. Just like the marks we get, okay, in schools. Understood this point? Okay. Okay, fine. Is this clear? So this formula is very, very important for us. Very, very important. Okay, because okay, I will give you a easy question first. Let's try if we are able to do this or not. It's a very simple thing. See, they're saying that the synthesis of N2 from NH3 and CuO has a theoretical yield of 10.67 grams N2 from the starting amount of reactants. From the starting amount of reactants under the same conditions, under the same conditions, an experiment produced 8.35 grams of N2. Determine the percentage yield, they are asking. This is the most basic question anyone can ask you. Most basic. They are giving you the theoretical yield as well here. See, they have also given you the theoretical yield. They have also given you that in an experiment, N2 is this much produced, 8.35 grams. So if you want to find out the percentage yield, it's nothing but you'd have to divide 8.35 by 10.65 into 100. You do. This is your percentage yield. I hope this is clear to you, which is 78.4% coming out to be. I hope this is 100% clear to you, right?
Yes, sir.
Okay. Then, now let's read this question, what they are saying. Okay, let me just, okay, let's do it here itself then. Yeah, CaCO3 is able to remove SO2 from waste gases by a reaction in which the two substances react in 1:1 stoichiometry to form equimolar amounts of CaSO3 and CO2. So if this kind of thing, stoichiometry, is related here, then first step was to write a balanced chemical equation, right? Remember? Remember, right? Write a balanced chemical equation out of it. That CaCO3 will react with SO2 to give me CaSO3 plus CO2. Is it okay for you? Now try to balance it out. Check if it is balanced or not. It's balanced already. I can see it. It's already balanced. Okay. Now, when 255 gram of CaCO3 reacted with 135 gram of SO2, 198 gram of CaSO3 were formed. Determine the percentage yield. So can you tell me what is given to you in practice? What is given to you in practice? Do you have experimental yield with yourself, with you, in the question given? Hello. Are we guys having experimental yield given?
In which, sir?
Yeah. Sorry?
In which, sir?
In the first question itself.
Yes, sir.
We have experimental yield given. See, this
Yes, sir.
198 gram of CaSO3 were formed. That means They are saying that if a reaction was going on, if experimental is going on, we are getting 198 grams of CaSO3, and they're asking us the percentage yield of CaSO3. So experimental yield I have at least, which is 198 grams. Can I calculate the theoretical yield myself? Can I do that?
Yes, sir.
Yes, we can do that using our basic concepts of stoichiometry and the limiting reagent. Now, did they mention anywhere that it is a complete reaction going on? No, haven't. They haven't. It's not a complete reaction. Completely reaction was not written over here, so that means this is a question of limiting reagent. Do you agree with me?
Yes, sir.
Yeah. Yeah. So we need to apply the concepts of limiting reagent. How to do that? How do we do that? First, we require the balanced chemical equation, and then we now know that 255 grams of CaCO3 I have and 135 grams of SO2 I have, right? We need to convert it into moles first, right? Convert it. Convert these to moles. If you don't know, I will write it. Calcium is 40, sulfur is 32, oxygen is 16, and carbon is 12. Convert this to moles. How much mole of CaCO3 and SO2 you are having? I think we are getting 100 as a molecular mass here and 64 for this. Do you guys agree?
Yes, sir.
So how many moles we are getting here? It is 2.55 moles and 135 by 64. It is how much? 2.1. 2.109. See, this is a 1:1 reaction, right? And now maybe you can check. Of course, the limiting reagent is, I am dividing it by the stoichiometry of my reactants, right? To find which is my limiting reagent. Of course, this value is smaller. So this is your limiting reagent. According to this now, your products will be generated. Do you agree with me in this manner also? Yeah.
Yes, sir.
This is my limiting reagent. According to this, only my CaSO3 will form. So if SO2 and CaSO3 have the same stoichiometry, or what you can do, you can read the statement first. After reading the statement, you can then decide that how will you read the statement that 1 mole of CaSO3 requires 1 mole of SO2 to produce 1 moles of CaSO3. So I am having 2.109 mole of SO2. So I will be getting 2.109 mole of CaSO3 as well. I hope this is clear.
Yes, sir.
And now you multiply it because we need to find out the percentage yield of CaSO3. I got the actual moles of CaSO3 by pen and paper. So this is my theoretical yield, but we need to convert it into grams because the experimental yield is also given to me in grams only. So I'll be multiplying this by the molar mass of CaSO3, which is how much? Into multiply with the molar mass. How much is the molar mass? Can you tell me?
120, sir.
Sure.
Sure.
Okay. So multiply 2.109 by 120. How much we are getting? We are getting 0. Sorry, no. We are getting 253.08. Do you agree with me? 253.08. So this is your actual yield which you calculated using your pen and paper, right? And this was your experimental yield. Divide the both quantities. 198 divided by 253 you do into 100. This will give you the percentage yield. I hope this is okay for both of you. It's not a difficult question I am saying. Okay,
Yes, sir.
Mrinal, it's fine.
Yes, sir.
Okay, cool then. See now. So will you be able to solve this question for me? We have to be a little faster because I need to start the atomic structure as well. Will you be guys able to do this for me? See what they are saying you.
Sir, try, sir.
Try. There is a reaction going on. CH3COH plus C5H11OH gives you this. A reaction uses 3.58 gram of CH3COH. Okay, this is given to me as 3.58 grams. And 4.75 gram of this is given to me. I'm just writing it. Okay. and has a yield of 45%. They have already mentioned that the percentage yield is this time is 45%. They are saying that determine the mass of ester that forms. How much mass of this ester is getting formed? That is the question.
So that means theoretical value they're asking, sir.
No, no, no. They are not asking theoretical value. They have mentioned that percentage yield is this much, right?
Yes, sir.
So of course, theoretical yield you can obviously calculate yourself using these values, right? You can check the limiting region yourself. You can calculate
Experimentally
the
they're
theoretical
asking.
yield. Sorry.
They're asking experimental yield, sir.
Yes, experimental yield they are asking you.
Yes, sir.
How much that too in terms of mass of ester. Is it okay?
Yes, sir.
See, if any data is given to you for the reactants, you can always find the theoretical yield yourself. They will never ask you to find the theoretical yield. If they're asking you to determine the mass of ester that forms in this reaction, it means that whatever the experiments they are doing, they're asking you the yield of that. Experimental yield basically. Okay, do it. Mrinal, are you able to solve? I am more concerned about you because you haven't attended the last lecture.
Yes, sir. I'll do it. I'll do it.
Okay, I want both of you the answers from both of you first. First of all, okay, take your time, do it. So anything up to now you got anything?
Moles of CH3CO was CH5H11.
Okay, so you got how much?
0.053.
0.5 596 I'm getting, I guess.
53, no, sir. It is C5H11 OH is limiting reagent, no, sir.
Oh, you are talking about this one. Whose mole you have calculated till now? Sorry,
The reactant side, first one, sir.
first one, na? So you have done 3.58 by 60 only, right?
Sorry, sir. Product side, first one I'm talking about.
Okay. So this is this value first of all,
Yes, sir.
and this is how much? This is I'm getting
53.
0.0465.
4.
No,
Sir. Oh,
no. Is it
just
wrong?
checking, sir.
C5H11OH. How much is the molar mass? 60 plus 12, 72 plus 16. Isn't it?
Yes, sir.
Or what? I have done something wrong.
Uh,
12 fives are 60, right? Plus 12. Sorry, 1 plus 16. 88 you are getting?
yes,
Divide
sir.
by the 88. Then
Zero
it's
point zero five three only, sir.
okay, okay, it's fine then. Okay. 0.053. Fine then. 0.053. Okay. So say the which is the limiting reactant now? Check it by dividing it by the stoichiometric coefficients.
C5
This is your
epsilon
limiting reactant. I got this mole 0.053. I said, okay, good. Then this is my theoretical yield which I got. Theoretical yield. I got it. The theoretical yield you can find out even in terms of mass or even in terms of moles. Mrinal, you are also getting the same thing up to here? Hello, hello. Yeah. So then, what will you do next?
experimental yield moles 0.023, sir.
So what you have done? 45% of this value. Yeah.
45 is equal to 100 into x by 0.053.
45 is equal to 100 into x divided by 0.053. Yeah, it's correct. Yeah. So you will be getting x from here, whatever.
Yes, sir.
Okay, that will be your
Moles.
moles of this, and then multiplied with the molar mass or
Molar
molecular mass
mass.
of this, you will be getting the mass of the ester.
Yes, sir.
Okay, I want Mrinal to tell me, is it correct?
Yes, sir.
Any doubts? Any doubts you have, please ask.
Sir.
Sorry? No doubts?
No, sir.
Okay. Can I move further? The value, your answer, you can reach up to your on your own, right? Final answer, I guess.
Sir, by using significant figure, how we do this, sir?
So you can you can know na that okay, we are having three significant figures here, three here. So you have to report the final answer in three significant figure itself.
So we should take a 0.0596 and 0.0538, sir, for calculation.
No. The end value which you are giving us as the final answer, that will be round off up to the three significant figure. That is the main concern. Okay.
While calculation, how many decimals should we round off, sir?
See, you will be getting the calculators there, right?
Yes,
You will
sir.
be giving the calculator. So while calculating, no need to round off as well.
Every question we can calculate, sir, in exam.
Sorry.
For every question, can we use calculator, sir, in exam?
For all questions you can use the calculators, no problem.
Okay.
Calculator is given to you. That's not a concern.
Yes,
So
sir.
don't round off while calculating. You have to round off up to the least number of significant figures in the end, in the final answer.
Yes, sir.
Okay, clear?
Yes, sir.
So whatever the value you are getting, I am not concerned here. Just round off up to the three significant figures. Now I want to give you a good question. Last question regarding this topic. Then this topic I am just ending now. Okay. The question is, yeah. So this you have to solve, both of you, yourselves, and if possible send me a picture on WhatsApp. See what they're saying. A student has to make 100-gram sample of chlorobenzene chlorobenzene C6H5Cl from the following reaction. Which is C6H6 plus Cl2 gives you C6H5Cl plus HCl. They are saying that determine determine the minimum quantity of benzene, benzene is C6H6, this, that can be used, that can be used to achieve this with a yield, with a yield of 65%. This is a very nice question. Very, very good question. This time they haven't mentioned you to find the mass of the product. They're saying you to find the mass of the reactant. How much reactant will you use so that you will be getting this product with 65% yield at least. Try. In the first line, they have mentioned you anything, something. Remember, a student has to make 100 gram sample. What is this 100 gram? Your theoretical yield or the experimental yield? If I ask you, what is this?
Experimental yield.
Very good. Now this time experimental yield is given to you. Percentage yield is also given to you. You can find the theoretical yield yourself. Okay, so now I gave you the hints. Please try to do it yourselves. Please try it. I want the answers from both of you. Sorry for today, the 2 hour delay from my side because I'm not well. Uh, I was not having some energy to wake up in the early morning. Never try to solve the question in terms of grams.
Sir, here, without having chlorine information, how can we solve?
You can solve it, no issue. Assume chlorine is in excess,
Like C6H6 is limiting reagent, sir.
of course.
But they didn't mention, no, sir.
Yeah, so if they have not mentioning it, either you can assume that they are given you in the equal amounts, or you can assume that this is an excess.
Okay.
You won't be getting any trouble here. So how much moles of this chlorobenzene do I have?
Sir, last set doing.
Okay, okay.
Sir, 106.08.
So are not 6 point.
08.
Uh, it's not the exact value, but
Ah, yes, I did approx, sir, in middle.
I don't want the approx value. I want the actual answer actually. But okay, it's fine. I think the exact answer is 106.76, which you should get. You might be rounding off somewhere.
Yes, sir. I did round off.
Don't round off. I am repeating again. Otherwise, they will give you a 0 mark. They don't give you any range to give the answer in this particular range. No.
Okay.
Mrinal, what about you? Hello. Mrinal. Hello. Yeah. Are you able to do this? If you are speaking something, I am not able to hear you. See, you have to be a little bit interactive for the class. Yes. What answer you got then? You, if you want, you can share with the image of the answer with me on WhatsApp as well. No problem. No problem for that. Just let me know. Okay, please send it then. I'm giving you 2 minutes to. If you have completed, I'm giving you 2 minutes to send the answer to me. Okay, so percentage yield questions are also given in the homework as well. So now you will be able to solve all the homework. There's nothing new for you. It's easy for you now to do it. First, first, first. Sending right? Or shall I move further? Mm. Minal, are you sending me? You can type at least. I don't know if you're here or not. So from next class, I want you both to turn on your videos at any cost. Okay. Today I am also not well, so I am not turning on my video. But it's not like that I will not never turn on my video. I will always turn on my videos. But you also have to do it from the next class now. I will not listen anything, any excuse that I will be doing in 5 minutes. No. From the beginning of the class, you have to do it. Okay. Today I am not saying you anything because myself, my video is not on. So I am moving further ahead. Okay, with the atomic structure topic. So please listen it carefully. Okay, atomic structure. So here I guess we need to study four things basic about the atomic structure, how to write the electronic configuration, then what is photoelectron spectroscopy, a dual nature of light and matter both, and one more thing, periodic trends. Okay, these are our most common topics which we have to discuss here, starting off with like discovery of electron. Who discovered the electron? Any idea? Discovery of electron. Who discovered the electron? It was J.J. Thomson who discovered the electron. And how he discovers the uh, J.J. Thomson? How he discovers the electron? I will show you some image. See, can you see this? So what he does is he took electrodes as cathode anode. He passed electricity from here, and then he saw that from cathodic side some particles are ejecting out. Okay, this is called a discharge tube experiment, in which from the cathodic side some rays or some particles are coming out. Okay, and then he thought, what are these particles? He was not sure, but he, like, one thing was sure here, that whatever the particles are getting released from the cathodic side, they travel in straight line from the negative pole from the negative pole of the battery, or cathode you can say, to the positive pole of the battery, to the positive pole, that means anode. Okay, they are getting removed from the cathodic side, they are getting going towards the anodic side, towards the positive pole. I hope this is okay. So then he was not too sure that, okay, why is something moving on to the anode, what is happening here. So what he does is he did something extra. See here, what he did, he again done the same experiment, but this time he applied some plates here. See, this plate, okay, maybe this plate, I will show here, this and this he applied. What is this? this is either, you can say, the plates are your electric field or magnetic field. He applied that. Okay, now the particle, the electron which was moving in the straight line, it reached up to a node, and after reaching a node, when it further tries to go, when it further tries to go ahead, it was it saw that, okay, there are two terminal sides of these plates. One is positive, one is negative. Now suddenly what happens is this got deflected towards the positive side of the plate and away from the negative side. Okay, can I write? Deflected its path. The whatever the rays which were coming from here, they were traveling in a straight line, as I mentioned, but suddenly when you apply the electric or magnetic field, it deflected from their straight line path. Okay, now it deflected towards the positive side. Due to that, we know that whatever the particle is there which was traveling in the straight line, it must be having a negative charge. That is the reason it was deflecting towards the positive charge and away from the negative charge, because like charges repel each other and unlike charges attract each other. Is it okay for you? This is fine. So can I say from this that deflected from their path if electric field or magnetic field is applied? Is applied. Okay. This was what was happening actually. How they discovered electron. Okay, electron, they know now that, okay, there is a particle which is a negatively charged particle which was travel in a straight line when there was no electric or magnetic field. But when we give electric or magnetic field in this apparatus in this manner, then this particle also got deflected towards the positive side, and this shows that the particle whatever was removed from the cathodic part was having a negative charge, and that's how J. Thomson found out the electron. I hope this is clear. This is a basic theory. Okay, then after that what happened is, then we are discussing now how someone discovered discovery of proton. So it was kind of a opposite kind of experiment in which the scientist Goldstein discovered that, okay, I will can show you this as well. Uh, yeah, see this one. Now what is happening? See, now this time, if you can see here, we are having a same thing, cathode, anode. But this time, some particles are get traveling from the anodic side. They are produced from the anodic side, and they are traveling towards the negative terminal to the cathodic side. Can you see this? Can you see some particles are moving from here to here and coming here, right? It's the same thing. The particles which were getting removed from the anode, they also travel in a straight line, but they go to the negative terminal of the this entire discharge tube or the battery. You can say they go to the negative terminal of the battery. So I can simply say that, okay, some positive charge species was ejected out from this side because it is going towards the negative side, and those particles were called as protons. Is it okay for you? This is also fine.
Yes, sir.
Okay, if this is clear, then what else they observed? For the confirmation of this, they have taken another set of example. This they see here also what they have done. They again applied a electric or magnetic field. Just a second. Yeah, they have again applied a electric or magnetic field here. See this one, maybe you can see again. A positive plate is there, a negative plate is there, and some particle is getting removed from the anodic side. Okay, that particle is now deflected towards the negative charge and away from the positive charge, right? So who will be attracted by the negative charge? A positive charge particle only? Of course, a positive charge particle only. But the problem is, in this case what happens? Yes, deflection of electron and proton both are occurring. We know that now deflection of electron and proton both are occurring. Okay, first of all, let's figure this out. Okay, so any particle, if it is deflecting towards the negative side of the battery or the negative terminal of the electric field or magnetic field, of course that particle must be having a positive charge with itself. That is, of course, obviously sure. But the problem here is that the proton, the whatever the particle which was this one, na, it shows less deflection. It shows less deflection. You can say it shows less deflection as compared to electron. It was the experiment. We can't do anything. See, if I ask you, okay, electron is showing how much deflection? Electron is going up to here, a very high deflection. But if I ask you, what about proton? Proton, they will say, okay, they will be going like this, very less deflection, very less deflection, very less deflection, they will be showing. But why is this so? Why the proton shows less deflection? Because the protons particles are heavy. The protons are heavy. They are heavy mass particles, due to which their deflection is also less. Is it okay for you? This is fine. So there were two conclusions from here, that electrons were having negative charge, shown by J.J. Thomson. Protons were having positive charge, shown by Goldstein. And also protons were heavy as compared to electrons. Is it okay? Can I now move to the neutron discovery? Yeah.
Yes, sir.
Okay. Then discovery of neutron comes into the picture. So now this neutron was a particle which was discovered by James Chadwick. Just remember the names of the scientists. James Chadwick. Okay. And it was discovered when beryllium atom, Be, was bombarded. Beryllium was bombarded. Bombarded means collided with the alpha particles. Do you know what are alpha particles? Any idea? What are alpha particles? This.
Positively charged particles.
They are positive charge, but it is actually the helium nucleus. Helium is 2,24, right? That means helium is having two electrons, helium is having two protons, and helium is having two neutrons as well, right? Now
Yes,
what they
sir.
have done, they have taken alpha particle. What is the alpha particle? Helium's nucleus. They have removed the electron from the helium atom. That means now this is not there. Only the two protons and two neutrons are there, and these are present in the neutron nucleus only, right? So helium 2 plus is nothing but the alpha particle, and it's a nucleus of helium atom. So this beryllium was bombarded with that alpha particle. So what happened? When this was happening, what happened actually? See, beryllium plus helium was 2 4, 2 plus, beryllium was 4 9. It collided and gave you something in a different element, X612. Now what is this X612? That is our first question. And it also gives me, okay, first of all, let's discuss only. So when this was collided, it gave me a element called X612. Which atom has 6 proton number and 12 mass number? Can you tell me that? Which atom has this thing? It was the experiment which was shown by James Chadwick, that when you collide beryllium atom with the helium nucleus, this was what we are getting. This is nothing but carbon atom, isn't it? C12, 6, C612. Do you agree with me? This was nothing but the carbon atom only. But now, if you see here, that here the proton number sum is 6, which we were also getting 6. But the sum of the mass numbers was coming out to be 13 here, but it was 12 only here. So there is some particle which was extra releasing from here, so to balance the total mass, because we know that mass can never be created nor be destroyed. So of course there was some kind of element which does not have a proton number or the atomic number, but it has a mass number only, something like this. And this was the neutron which was removed from here. Because when I collided this beryllium with helium nucleus, I am only getting the carbon as my atom, nothing else I got. So of course, if the mass can never be created nor be destroyed, so this mass 13 to 12, one was still left. Some different particle must be released so that the mass conservation should take place, which was this atom. Not this atom, this particle. This is called neutron. This is how neutron was discovered. Is it okay for you? Neutron
Yes,
discovery is
sir.
also fine?
Yes, sir.
Okay. Okay then. Then let's go to further. Now, many scientists came and they tried to find out actually that what is the atomic models, like how a atom looks like actually. How does an atom looks like? Okay. So first, okay, atomic models I will write as a heading. Atomic models. The first model was given by J.J. Thomson, called as Thomson plum pudding model. Plum pudding model. What it suggests to you? It just simply says that, okay, I will be having a pudding. I have a pudding kind of thing, or you can also say watermelon seed model. You are having a pudding. Pudding is like this, and I am having plum seeds in it. Plum seeds like this, like this. This is my plum seeds. Okay. Now, whatever the plum seeds, the small dot which are represented here, whatever the seeds are there, na, those are your electrons, which are moving inside the whole plum. Okay. And the rest of the thing, which is this area, which is all this area. How to decrease this size here? Just a second. Hmm. Which is all this area which is empty here. This all area, the empty area basically, this is your complete positive charge. It carries a positive charge at all times. Is it okay? This complete area carries the positive charge, and like the electrons are like seeds which are just embedded into this positive charge. I hope this is clear to you.
Yes, sir.
Yeah. Okay. So this what Thomson says, but this model has very large number of limitations. Okay, so this was exactly failed because after this another model came which was of Rutherford. It gives you some even deeper idea regarding how atoms should exist. So the second model which was given by Rutherford was a little bit a better model. Rutherford's model, it was a better model because Rutherford has done some experiment. The Thomson has just said you that okay, this is how atom should look like without doing any experiments. Thomson has said that, but Rutherford has done some experiment called the alpha particle scattering experiment. It is called as alpha particle scattering experiment. Let me see it if I have the image. No, I don't have. Okay, fine then, no issue. So what Rutherford does, Rutherford has taken a very thin gold foil, a very thin gold foil. Okay, and then he tried to like bombard this gold foil. This was a gold foil, and tries to bombard this gold foil with again the alpha particle, which we know now is the helium nucleus, nothing else, right? It is the helium nucleus. That means it is bombarding it with a positive charge species. Do you agree with me? And this gold foil is very thin, very thin. It is about the 100 nanometer thickness. You think now 100 nanometers, how much less thick it is actually. Okay, and what else it has? It has a big detector. It has a very big detector. It is hole detector. It is done in a complete closed space, and a closed space is all your detector. Is it fine? Yeah. Detector, deflection screen, detector screen. This is your detector basically. Okay. Now what happened? What he observed? What was the observation? When he tried to like bombard this alpha particle onto the gold foil, the alpha particle uh, it went into the straight line. Sometimes what happens is it went into the straight line directly like this. It went straight. It gives you some it gives you some reading over here that okay, the particle got detected over this side. Okay, again it can get onto the same side. Straight line it is going, maybe I am saying like that. Okay, or what happens is this particle which was going from here, coming from here, also gets deflected a little bit through some angle. From here as well, from here as well, it is getting deflected by some angles. Then even it is getting, sometimes it gets more deflected also. More deflections were seen, and a 1 lakh particles, like it when alpha particle was going in this direction, 1 out of 1 lakh particles was came back at the in the exact same path. and gave you the reading, like gave you the signal here that okay, the particle was restricted here. The particle was going everywhere, but the percentage of particle which was getting deflected were less. The percentage of particle which was going in the straight line were more, and the percentage of the particle which was coming by the same route back from where you have thrown it was just 1 out of 1 lakh. Are you getting this point as well? Yeah.
Yes, sir.
So it means what? See, you are throwing a positively charged species onto a gold foil. So what happens at the gold foil is, if you know any atom, how an atom looks like, an atom has normal. I'm asking you, an atom has what? An atom has a nucleus, and electrons are, we know now, right? An atom has a nucleus and electrons are like traveling like this, right? So Rutherford gives this answer that okay, most of the particles of alpha particles which were going into the straight line, they were very far away from the nucleus. That is why they are not getting any deflections from the nucleus, because nucleus is also a positively charged species. The particle which you are also bringing, the helium particle, was also a positively charged species. Few particles of helium positive which were going from nearby to the nucleus, they gets deflected, because positive charge, they will be repelled like this, they will be deflected. I hope this is clear. And one out of that thou lakh particles which directly gets bombarded to the nucleus of the atom, of the gold atom, it simply goes and comes back from the same site. Is it okay for you? Yeah. It simply goes and come back via same path, because it was a head on collision, it was a direct collision which occurs, due to which it came back here. I hope this is clear to you. So Rutherford was right that okay, if this is the situation, if something like this is happening, then that means at a very small space, at a very small space, your positive charge is residing. Positive charge is residing. Is it okay for you? Yeah. Because at every time, see, if the positive charge is present like this, if what Thomson said, that the positive charge is everywhere, if this was a situation, then from wherever you throw your positive charge helium alpha particle, it will come directly back from the same direction, because it will be repelled from each and every direction and it will be coming back. But it was not the case. When he did this experiment, only 1 out of 1 lakh particles which were directly getting collided with the some heavier positive charge mass, these were only getting back via same path. So that is what, how we find that okay, the positive charge was residing at a very small space. Is it okay for you? And he also mentioned that electrons are revolving around the positive charge, but he does not give any explanation. He just mentioned that electrons are revolving around the positive charge. There was no explanation for this concept. Are you getting this point? Okay. There was no explanation for this as well. Okay. So I am writing few points for the Rutherford model. Please try to understand this. The first point was that the positive charge, most of the mass of the atom was considered in an extremely small volume. This region is called as nucleus. Most of the mass of an atom was concentrated in a very small volume. Okay. And this region is called as nucleus. This was an interpretation of Rutherford, which was totally correct. Nucleus is taking a very small space in an atom. Okay, and all of the atom's mass was due to this nucleus only. Okay. Then Rutherford also proposed that electrons are negatively charged particles which were surrounding the nucleus and revolving there. Okay, in a high speed, in a circular path. So I can simply say electrons revolve around the nucleus in circular paths. I hope this is also clear to you. The third thing, it said that electrons, because there was no explanation for this concept, so then he said that to explain this theoretically, he said that electrons being Negatively charged particles are basically attracted attracted by the nucleus via strong electrostatic force of attraction. Do you agree with me in this? Tell me, is it fine for you this much?
Yes, sir.
But there were no explanation neither given to this part, neither given to this part. This we know. This was the experiment. So this theory was correct, but there was no experiment regarding the electron. So we can't say that this is 100% correct, which was actually not. Okay, which was actually not. So who gave that? Okay, this is wrong. See, there was a scientist called Maxwell. Maxwell was a very big scientist. It came and it says that any charge particle, any moving charge particle, let's say you are saying, the other four was saying that electrons are revolving in a circular path. If this is the case, that any charge particle is moving, then that charge particle releases some radiations, some radiation loss, release some radiation. That means energy loss is occurring at every point. Okay, it means what? If Rutherford was saying that okay, electron were revolving in a circular path around the nucleus, then this moving charge electron is constantly losing its energy, and if it is losing its energy, it is going like this, and finally it will be collide. That electron will collide with the nucleus, and the atom will be destroyed. Atom is getting destroyed. Think, Maxwell said that if any charged particle moves, because Maxwell has done an experiment which shows that any moving charged particle releases energy. It loses energy. So if something is losing energy, of course it is getting, uh, you can say it is getting more closer and closer and closer to the center. Do you agree with me? Yeah, because it is losing energy, right? So see, if you are having more energy, you can move like this. If you are having less energy, you will be moving like this. If your energy is gone, it will be you will be staying at the center. This is what happens usually. Okay, so that was Maxwell's like what Maxwell said, which was actually true. If this kind of situation occurs, then the electron must get vanished, the atom must get vanished. So the Rutherford's model, which in which he said these two things, was totally wrong. I hope this is also clear to you. Okay, this was a drawback of the Rutherford model, which does not able to tell you actually how is the electron moving, where is the electron. We don't know anything up to now. Is it okay for you? Yeah. Yes.
Yes, sir.
Okay. Now the rest of the thing I will tell you in the next class. But one thing you should know, that do you know na, that electron charge is what? The charge on one electron is 1.6 into 10 to the power minus 19 coulombs, right? And we also know that okay, this is in minus, and the charge on the proton is what? Positive 1.6 into 10 power minus 19 coulombs. So these charges, how someone calculated these charges? This were done by the Mullikans, scientist called Mullikan, using its oil drop experiment, which we should not learn because it is not a part of our syllabus. Is it okay for you? So till now, like what Rutherford and Maxwell combinedly says, Rutherford says that the positive charge nucleus is present in between the atom, which is totally correct. It is a heavy mass particle also, the nucleus, but these electrons, we do not know where are they. Whatever the other force says was totally wrong, because electron in constant motion always releases energy, due to which it will be electron will be collided with the nucleus and atom will be destroyed, which was not happening. If all the atoms, see, whatever you guys are using, wood, your pencil, your scale, whatever you are using, they are all made up of atoms, right? If if a atom is getting destroyed, then those substances, the things which you are using in your daily lives, they will be getting destroyed maybe in less than a second. Then the earth will not exist, which was not the case. That means the Rutherford theory was wrong. So then comes, to correct this, comes the Bohr theory, which we will start in the next class. And from there only we will start the dual nature of matter. Okay, dual nature of matter and light. I hope this is clear. Please do the homework. You are having a lot of homework now from my side. Please try to complete it by the next week, by the Sunday. Okay, fine. Any doubts you have? Any doubts?
No, sir.
Okay then. Fine, then we'll meet later. Bye bye.